Welcome to the second half of chapter 2. Actually, it's not a half, it'll be a third. I've taken acids and bases out of this portion of the lecture. I'm going to do a separate video for that one. This one will be primarily about the properties of water. So here I chose to start with this slide. I took it out of the last one. It was not sequenced correctly to me. I don't know why. In my brain, I just wanted this to be one of the first things that we talked about before we go into H2O and how universal it is. Universal in the sense of like so many species need it to survive, and the planet Earth thrives off of it. So before we go into something that's like common between everything, let's talk about elements that maybe are not so common among all living things. In other words, we're looking at elements from the periodic table that could be harmful to some species and the exact opposite for others. So they could be very helpful to a different species. Very quickly, I'd just like to point out two examples and I'll keep moving. So in humans, arsenic is something that can be lethal. It has the potential to kill you. There is a place in California called Mono Lake, and if you look at any photos of this place, it really looks like it's not on the planet Earth. It looks like it's something out of a movie script where, I don't know, you'd be like on the planet Mars. It is very desolate. There's no green vegetation. It just looks like nothing lives there at all. But there were some, I guess, I don't know if they were doing like an ecological study or what the situation was, but someone happened to come across the fact that there are these archaea that are residing in the Mono Lake lake. And so there's high levels of arsenic in this lake, and these archaebacteria or archaea, they thrive off of the arsenic. They actually use it to metabolize and make energy for themselves. So they're doing something called chemosynthesis. They're like using the arsenic to fuel themselves. They thrive off of the arsenic. So the very same element that could kill us is helping something else in this world thrive, and that's very interesting. So a second example where you can kind of see an evolution of tolerance to a toxic element is with the sunflower plant. So sunflowers are able to kind of take up a lot of heavy metals, like large amounts of heavy metals, without being harmed. And this is helpful if there's ever a disaster in an area where the soil content for some reason would have large levels of zinc and some other heavy metals, like how they list here, lead, zinc, and many other heavy metals. And so what scientists have done is they've taken the knowledge that sunflowers are able to do this, and they put them in places where they can help clean the soil. And so one place that they put it very recently, or when I say very recently, I mean like it's not from like 30 years ago. When Hurricane Katrina hit Louisiana, they went in after, I guess, some of the cleanup, and once they could get the levees situated and get some of that water out of there, they plant these sunflowers, and then they help to make the soil back viable by taking some of the heavy metal out of it. Same thing was done in the Chernobyl nuclear disaster. If you don't know about either of these historical events, please go look them up, check them out. Big stuff. Alright, so why is it that these molecules, their shape and their function can affect a living thing, well, one living thing one way and another species or living thing a different way? And I use the example of the natural endorphin and the morphine. I did this one in the previous playlist, or in the previous video for this playlist, and so I'm just going to fast forward really quickly. The only thing I would like to point out is that there are 3 elements in this region here and 3 elements in this region here that make up these 2 molecules, so endorphin and morphine. And those 3 molecules are oxygen, carbon, and hydrogen. The whole back half of these look very different from each other, but that's not even the part that we have to focus on. The part that we're focusing focusing on is just that black box part. So in this picture, if you did not see the last video, I'm showing you now. But if you saw the last video, you might want to just like fast forward me a few seconds, maybe a minute. So this area here, that's the cell membrane. So that's the boundary that separates the outside from the cell from the inside of the cell. This area in here, so this is the inside of the cell. So if something needed to get into the cell, it would come from the outside and it would go in. This big purple glob, they're calling them endorphin receptors. They're proteins, they're embedded in the cell membrane. And so what you're seeing is they're showing you, like, look, natural morphine can bind with this receptor in that area. Or excuse me, natural endorphins can. I was looking at the morphine molecule. And then morphine can also bind with the same type of receptor. So what does that mean? It means that when people are in pain, if they were to take an endorphin, it would make them, first of all, it would ease their pain. It could make them also feel happy. And this is kind of like significant, especially now, because you know they talk about like, oh, there's this opioid epidemic that's happening with painkillers, prescription painkillers. This is the kind of thing that will make a person's brain chemistry be out of whack if they were to be taking such a hardcore painkiller on a daily basis. So here you see morphine is linking. If you flood your brain with this morphine or any derivative of it, so like any of like the oxycontin, oxycodone, hydrocodone, like all of those that class of drugs, they mimic these endorphin molecules, and it can trick your brain into thinking that it doesn't need to actually produce them by itself. And so over time, people become addicted because their bodies are physically used to not having to produce these natural endorphins. Why would it need to waste time on it if you can just take something and then it would flood the brain? So that is the chemistry behind, or just like very surface level chemistry behind what is going on with that whole situation. Alright, so let's talk about the first property of water that we're gonna need to know about for our test that's coming up sometime next week. Usually, I think the end of next week is when most of you are testing. So water molecules are polar. That's the first thing. So polarity simply means, just think about poles, like poles are like opposite. If I say something like the north pole of the earth, and then the other part would just be the south. It's always like the opposite end. So polar molecules, they're going to have an opposite end. One end will be partially negative, and one end will be partially positive, or slightly positive. And for H2O, those regions are as follows. So the red balls are oxygens. All of these are oxygen molecules. Bam. Oh, that didn't highlight well. Let's do this color. Yeah, oxygens. So all those are oxygens. Oxygens are carrying this partially negative charge, and they designate it right here. Partially negative, partially negative, partially negative, partially negative. All around the oxygens. The hydrogens are partially positive. So here you have one, so the hydrogens are these white balls. So partially positive, same here, same here. And so what you're seeing happening is the negative ends of the oxygen are attracted to the positive ends of these hydrogens of differing water molecules, and this is going to cause hydrogen bonding to happen. I discussed hydrogen bonds very briefly in the last. I was just saying that I kind of talked about hydrogen bonds in the last presentation because we were ranking like the strength of the bonds, but I also talked about why hydrogen bonds work so well, like in the bonding that they do. So let's keep going. So there's some emergent properties that water is going to display. So there's that phrasing again, emergent property. So here are a few that the authors point out. One is the ability of water to stick to other water molecules. So that's cohesion or cohesive behavior. So it's H2O sticking to other H2Os. All right, the second thing that they point out is that H2O has the ability to moderate temperatures. So why is that? It has to deal with the hydrogen bonding. It has to deal with the amount of energy that you have to put into separating water molecules. And when I go to that slide, we can talk more about that. The other thing that's big is that when water freezes, everybody knows when water freezes, it becomes ice. And what's interesting is that the solid form, so ice, is less dense than the liquid form. Say that again, that the solid form, ice, is less dense than the liquid form, meaning ice floats in a cup of water or in a lake or wherever this frozen water is going to be, this ice is going to be. And that is not usual. It's an unusual property. But it's important for life in lakes. And then the fourth thing they talk about here is how versatile of a solvent water is. So when you do the water properties observation in class, you'll notice that the term universal solvent is used, but I use it with like air quotes because it's not that it can dissolve all things, it's just that it can dissolve more than most solvents. So again, they do the cohesion business here. So the molecules stay close together because of cohesion. Water molecules are linked by multiple hydrogen bonds. So H2O plus H2O, that property of them sticking together is called cohesion. So water has cohesive forces. All right, adhesion means something a bit different. So you're talking about water sticking to things that are not water, but they have to be polar in order for the sticking to happen. Anytime you encounter something that is non-polar with water, the two do not mix. And a great example of that is oil and water. So oil is non-polar and water is polar, and so therefore the two just they can't combine. All right, so this idea of adhesion and cohesion, they apply it to something that maybe a lot of people don't put a thought into, but if you look at how tall some plants can get, like a tree, and you know that the roots of the tree are what is absorbing the nutrients to take up the tree, it's like really they're defying gravity. Like the ability of these trees to have the water move all the way up to the top, because that's where it's going, it goes against gravity. Like it just should not happen. So then the question becomes, well, like what is actually going on? There are these tiny tubes inside of trees. They're called xylem. And the xylem is able to, in effect, grab one water molecule, and then because of cohesion, another water molecule is, dragged along. It just gets pulled right up with it. So that's the cohesive force that's happening to contribute to this. It's called capillary action. But there's another thing that's happening. The water molecule is also sticking to the sides of the xylem. So here is the picture of that. So you can see water to water, there's cohesion. And then this water molecule being able to stick to this side of the xylem is adhesion. And these forces force the water up the tree. And trees kind of do some sweating. It's called transpiration. They release the H2O molecules back out at the top. Okay, so let's move on to another property, surface tension. So surface tension, Your book defines it as, let me switch back to the highlighter in orange yellow. Surface tension is a measure of how hard it is to break the surface of a liquid. If you think about the way water looks, imagine a small fly landing on it, or there's certain animals that can kind of like rest on the surface of water and they don't break through it. Water appears to have like a film. That's kind of what it looks like. So surface tension happens because of cohesion. So we're still dealing with cohesive forces, but this is another property that is worth looking at. This animation here is something that I wanted to be able to play, but I don't know if it's going to work. Yeah, I don't think it will work. So I'm going to pull this one out. I will say this. If you are able to log into the eTextbook site, there is a study area, and in the study area they have these things called BioFlix, and they show you, like, from this whole reductionism perspective, they'll show you like the entire tree in this case, and then they zoom in and they show you at a atomic level what is happening inside as far as this animation would go. So next slide is the BioFlix presentation, and again, I don't believe that I can click it to make it play for you, so please check that feature out, even if you're not really into reading the e-text and this is what you're listening to instead. All right, so another thing that H2O is capable of doing is moderating temperature. So one thing about water, large bodies of it takes a lot of energy to heat them up, and once they become heated, it takes a very long time for them to cool. So what they're talking about here is how water is absorbing heat from warm air and then it's releasing heat into the cooler air. It's this idea of like molecules and temperature. So again, it's not necessarily that something is being heated up. It's just a transfer of, or a taking away of heat from one substance into another. Or in this case, if the air is warm, if it's warm outside, the water will absorb some of that warmth in the daytime. It captures it, and then at night, once it gets cooler, that heat that's captured will be slowly released. So the important part is that water can absorb or release a large amount of heat with only a slight change to its own temperature. So again, it takes a lot to get it heated up and it takes a lot to cool it down. So here's the whole kinetic energy, thermal energy, temperature, and heat situation that I spoke about once before. Gonna keep going through. Let's really briefly talk about calories. So, and I do mean calories as in kilocalories, like the ones that are on your food packaging. So a calorie, this is what you need to know. It's the definition. There's nothing else for me to say here. It's just the amount of heat that you need to raise the temperature of 1 gram of water by 1 degree Celsius. And then the kilocalories, so this is again this is actually the calories on our food packaging. So 1 kilocalorie, because kilo means 1,000, right, is actually 1,000 calories according to the definition in the bullet point above. And then they talk about the unit of measure for energy, which is the joule. Let's keep moving. So this is a property that you will be able to see. I demonstrated in the properties of water observation station thing. If you had 7th period today, then you've already seen this, or if you're looking at this and it is, I guess it would be Friday, then you would have also completed the lab, and what I'm saying would make sense. But basically, water has a really high specific heat. It takes a lot to get it boiling, and by a lot, I mean there are things with way lower specific heat that will essentially catch fire with no problem. Water is not going to catch fire, it's going to evaporate. So specific heat is, again, here's another vocab thing, is the amount of heat that must be absorbed or lost for 1 gram of a substance to change its temperature by 1 degree Celsius. So the specific heat of water is 1 calorie per gram times degrees Celsius. And this is about the resistance that H2O has to change temperature because of its high specific heat. In other words, it takes a lot to heat a large body of water. If you think about filling up a pot with H2O, put it on the burner, it doesn't instantly heat up. And the reason why we use metal typically in the kitchen when we're heating or boiling H2O is because it's a good conductor. So it'll take on the temperature of whatever your pilot or your electric stove is putting out. So yeah, it heats up pretty quickly that way, just because you're directly hitting it with all this kinetic energy from this warm metal. So water's high specific heat, like I was saying a couple slides back, it's attributable to this hydrogen bonding. It takes a little bit to get it to break. So it's not the weakest, but it is not a really, really strong bond. It becomes more rigid when water turns into ice, and it becomes more fluid when ice is turning into liquid, and then they get real loosey-goosey when they turn from a liquid into water vapor or a gas. So what happens is this kinetic energy, or the energy of motion, which is coming from this heat, it's being absorbed when the hydrogen bonds break. And then when you want them to cool, when you want water to cool, it's the opposite. But heat is released from when these H bonds are formed. So this is the second half. This is the cooling part. Heat being released and heat being absorbed. And if you step back for a second, I don't literally mean that, but like just pause for a second and think about what I just said. Notice that I'm not talking in terms of cooling. I just said heat is absorbed or heat is released. So the absorption of heat breaks bonds, and then the release of heat would be forming bonds. And if you need more clarity, we can talk about it in class. Alright, so this is why when people live next to like large bodies of water, there's not a whole bunch of temperature fluctuation. So just look at this graphic really quickly. They're showing you California, so you're looking at the West Coast, Santa Barbara, Los Angeles, and in the Pacific Ocean, they show you a temperature there, San Diego. Notice that these points here all have temperatures that are about in the 70s, right? Comfortable 70-degree range. That's a pretty nice temperature to be living in. But then as you travel further inland, so you're going further and further away from H2O, it gets really, really hot. And the reason for this is that body of water, the ocean, is able to hold a certain amount of heat, and it's only going to release a certain amount of heat each day. But because it takes so much for water to boil and freeze, it just is not going to cool or heat up as much as these landlocked areas. If you were to run some kind of simulation where you had like a thermometer in sand versus a thermometer in water, and you expose them both to the same heating conditions, that sand is going to heat up a lot quicker than the water will. And then when it's time for it to cool, the sand is going to cool a lot quicker than the water will. Water is more resistant to change because of its high specific heat. Important water property. Okay, so there are 2 vocab words on this particular slide that you should just note. Heat of vaporization. So this is the heat a liquid must absorb for 1 gram to be converted into gas. So this is literally boiling H2O to the point that it becomes just water vapor. And then you have evaporative cooling. So it says as a liquid evaporates, in other words, as it goes from its gaseous form, its remaining surface is going to cool down. And they call that evaporative cooling. This is why you sweating is awesome when you're hot, because once it evaporates off the skin, you should be feeling a cooling effect. Oh, okay, I didn't even look at this bullet point, but this is exactly what I was just saying. Evaporative cooling of water helps stabilize temperatures in bodies of water and in organisms. All right, now we're on to the density part. The fact that liquid water is less dense than the solid form. So the solid form, ice, is able to stay on the top. It's very, very important that it freezes this way. If it did it from the bottom up, or let's say it froze from the top, but it was more dense, can you imagine a sheet of ice like on a pond or something not being too dense, basically, and then crushing everything below it? So here, if ice sank, all bodies of water would eventually freeze solid. That's one thing that's an issue. The second thing is you would crush everything below it as it was freezing. That would be terrible. So here's a picture of, I guess this is krill, some kind of small aquatic organism. And here it's showing you the bonds or hydrogen bonds. They're breaking and reforming. They do this in the liquid. They can slide past each other very easily. But in the ice, it's a lattice structure. So if you notice, like, perfectly spaced in between each other, the polarity is the reason why they're oriented the different ways, but it gets stuck in this formation. And this expansion is why it is less dense. It's like taking up more space. So you can see this if you were to put like a bottle of water in the refrigerator. The level of the water before you put it in the fridge, before you put it in the freezer, would be lower than after you were to freeze it and take it out. Do your own experiment. Try it. I'm telling you. And that's why sometimes if you overfreeze your water, the bottle looks like it wants to rupture. It's because of the expansion of the water molecules when they become solid. All right. Some more vocab words. So a solution, a solvent, solute, and an aqueous solution. This could be review. So a solution is just a homogeneous mixture of substances. So things have to be in equal distribution. So they're just like equally mixed. Think about pouring some salt in a glass of water. You stir it up. Salt crystals are not still at the bottom. They are evenly distributed throughout the water. That would be a homogeneous mixture. A solvent is what does the dissolving. A solute is what needs to be dissolved. So let's do the salt water again. In salt water, the solvent is water. In salt water, the solute would be the solid salt crystals. An aqueous solution is just water-based. So water is the solvent in the aqueous solution. And so let's talk about what this looks like. So why is this, why can water take this solid crystal structure and break it down so that it's no longer a solid crystalline structure? Well, the reason is because of polarity. So because sodium chloride, sodium takes on, it becomes a cation. It has a positive charge. It loses an electron, right? And then chlorine is an anion. And so what happens with it when it dissociates or when it breaks apart is that it becomes more negative. It took that extra electron from the sodium. And this unequal charge distribution is like preyed upon by the electronegativity of the oxygen atom and then the partially positive charges of the hydrogen atom. So they form these things called hydration shells. So here's what they look like up close. So this here, that is the salt crystal. They're doing the whole reductionism thing again. Bam, there it is, salt crystal, big. Notice that the chlorine molecule with the negative, so this is the anion that I was talking about here. It's being surrounded by H2O, but notice how they're oriented. The positive pole of water is attracted to that negativity of the chlorine atom. And then in the sodium up here, notice that it's all oxygens that are creating this hydration shell. So that's what's happening with the dissociation there. surrounding the anion and the cation in that ionic salt crystal. Let's see. Water can also dissolve compounds made of non-ionic polar molecules. Let's just keep moving. They give you an example, like proteins. There's certain proteins that can be dissolved in water if they have ionic and polar regions. So we'll see what that looks like. So here's an example. So the purple thing is the protein that we're speaking about. And notice that there's like a partially negative charge in parts of it, partially positive charge in parts of it, and you get the same kind of deal, where that negative oxygen is seeking out the positive parts, and it kind of breaks the molecule down from like that angle. And then the partially negative charges that are a part of this protein that we're looking at, the hydrogens are coming in to kind of create that hydration shell. So there we go with that. All right, 2 words important to know: hydrophilic and hydrophobic. Philic is loving, so hydro is water. So they're substances that love water, or they have an affinity for water. And then you have hydrophobic, so water, and then phobic is like scared of. So this is they're the opposite. They don't like water. They do not have an affinity for water. So oil is something that is hydrophobic. And the reason it's hydrophobic is because it is nonpolar. It can't mix well with those partially negative and partially positive charges, because there's no partially negative and partially positive charges for the outside of this oil to mix with. Alright, all of this is more chem review. Chemical reactions depend on the concentration of solutes. I think that is something that you guys should remember. You know, once all of the reactants are used up and the products are made, the reaction could stop, or we could reach a situation where it's chemical equilibrium. So the reaction kind of just has reached a point where the rate at which the reactants are being pulled apart and put back together is equal. Alright, molarity. This is something I need you guys to go back and look at. I'm not going to do a thing on molarity. Please go back, scour the internet, look at Khan Academy, something like that. You guys should know how to calculate the molarity of different solutions. There is a milk lab that we do, I believe it's for chapter 3, and molarity will play a part.